Welcome to Class 6. We'll talk about color grading. You already know a fair bit about RGB, and RGB is available as one of the displays on a typical or even special grading system, just showing a waveform monitor diagram from reference black to reference white, showing individual red, green, and blue components. You're now familiar from last class with the CBCR hexagon presentation of a vector scope, and so we know something about hue in CBCR space with the grayscale component projected all onto the same plane. And there's various controls available in color grading systems that are really variations on y equals mx plus b to the g, where x is the input value, independent red, green, and blue channels, and y is the output value, independent red, green, and blue channels. So let me, in this class, briefly walk you through the block diagram of very basic conceptual color grading, which I hope will give you an understanding of the importance of and how to operate sophisticated grading systems like the ones that are available for producing HD and digital cinema. I could start talking about grading by just giving you the block diagram of a grading system and talking about the ingest and then the approval and mastering stages. But first I have to cover off a conceptual element of grading, and that is that in a traditional HD camera, there's a curve, and it's our familiar curve taking 18% on the physical scale up to about 0.5 on the perceptual scale. But keep in mind that diagram that I showed you the other day of camera response characteristics, which are variable by adjustments in the camera. And these are the various gamma adjustments available on all kinds of different cameras. Now, typically the way that HD has been done in the past is that the camera operator, videographer, cinematographer, DOP, DIT, whoever it is that's got responsibility for shooting the scene, will crank those knobs to achieve the desired appearance on a display. So in other words, this gamma correction circuitry, which is incorporated into the HD camera, is delivering at the camera output signals which are directly suitable for application to the display. And this philosophy is called display referred. And the image data is said to be in the display referred state. Now, this scheme is not very friendly to VFX, because if adjustments were made in the camera that aren't available and aren't tracked and aren't reliably conveyed by metadata, then when you try to do VFX, really you want to reverse out these camera manipulations and go back to the light space that is represented by what's in the scene. And so I'll place my generic walking person here and say what you really want is these light levels, and what you'd like to do in many productions is capture scene referred data. And even if that goes through a curve, which is the normal state, because you want to take advantage of perceptual encoding to reduce the bit depth, reduce the demand on the storage and data transfer. Then what you'd like to do at the front end of DI is simply invert that curve. And these curves are just mathematical inverses. And ordinarily, you would choose a log curve to make that shoot. At the ingest stage then would be an anti-log, or an inverse log, whatever you want to call it. And often the log curves, which we'll detail in a later class, are specified by equations, which are just directly invertible by anybody who knows math. So the traditional way of doing HD does not do this. Traditional HD produces display-referred data, but for high-end production these days, we'd really like to have scene-referred data. So in grading, and I'm about to launch into the big discussion of what goes on in grading, there's two big concepts that you have to keep in mind. If you're ingesting display referred data from an HD capture, then grading doesn't really need to do very much. I mean, you can do white balancing, you can do increase or decrease of contrast and colorfulness as suits the aesthetic of the piece. But the input data is display referred, the output data is display referred, not much goes on. But on the other hand, if you're grading a scene referred, scene linear shoot, like probably a log shoot, then it's common at the front end of grading to invert that back into linear light space and then do some grading operations whose mathematics is complicated. And at the very end of the process, go into a display space, because all the standards that we're used to for distribution and display are based on power functions, not logs. So I'll use my log example. And so we've got standards like DCI, which has got P3 gamma and 2.6 gamma, HD, which has got 709 color gamut and 2.4 gamma. And, well, you know, we can also distribute out to sRGB or to consumer electronics, but really what we do in that case is just take the HD signal and interpret it with 709 color gamut, the same as the standard, but now interpret with 2.2 gamma, because the viewing conditions and the display conditions are different. But in any event, in all of that, at the output of grading, we're coding into a standard space as appropriate for the deliverable. So the key point in this preamble to grading is just that you need to know what kind of data is coming in. And certainly the knobs that are available to you in the grading system allow you to cover all manner of sins at capture, including compensating for different capture color coding, compensating for gamma or log capture, covering up technical errors, and so on. But the key point is you really need to know when you're coming into grading whether you're coming in with the display referred HD model or the new sort of scene referred digital cinema model, more appropriate for VFX shoots. So there's the quick conceptual diagram underneath grading. And I'll say one more little piece while we're on this slide. You know, there's some curves that you can select in the camera. And I'll pick a particular example, Sony Hyper Gamma. So this curve is advertised. There's several flavors. I think they're now up to 8 flavors, at least 4, but I think it's now 8. Hyper Gamma 1 through 8, and you know this curve is advertised by Sony as being suitable for high dynamic range and great contrast and blah blah blah, all this other stuff that's great. But the problem is it isn't the 709 curve. So you're not really delivering standard HD. Really, it's imposing a bit of an artistic interpretation of HD. You do directly ship this data to a display, and so it is sort of pretty picture math that's been included in this curve. And it can look fine, and it can be a perfectly suitable space. However, Sony does not tell you what the inverse curve is. So if you try to use hypergamma in a VFX shoot, you're in trouble. You don't know how to invert it at the front end of the grading operation. Now, people have shot movies in hypergamma, but the VFX and CGI work on those movies is a nuisance because the VFX and CGI has to, well, really the VFX has to figure out how to invert that curve, even though Sony doesn't tell you how to do it. Now, it's a better move to acquire such a movie in S-Log, you know, also from Sony, but they give you the equation for S-Log. They tell you exactly how the camera processed those signals, and you, at the front end of VFX can do the inverse S log just based on that math. So, again, keep in mind, whether you're shooting HD, which is intrinsically display referred, honestly, grading is fairly easy in that case, or whether you're shooting scene referred, in which case the overall block diagram is much complicated. Now, when you come into the totality of the grading system, let me do the block diagram of the overall grading system again. So you've got some sort of ingest capability, and there may be some color transforms and lookup tables at the front end. There's going to be some color transforms and lookup tables at the back end. And what's left is a bunch of adjustments. Now, we'll take my usual story of having the number 1 being reference white and the number 0 being reference black. And as you've already heard, there's lots of different alternative coding systems, so you'll find lots and lots and lots of people telling you, no, that Poynton, he's a crazy guy. Well, everybody in HD knows that reference black is 64, and I don't know why Poynton keeps talking about 1.0, because really reference white is at code 940. Well, that sort of argument really is limited to 10 bits. And that really is an interface standard. That's not necessarily what's going on in the guts of the grading system at all. In fact, it's increasingly common to have really wide floating point paths, sometimes even 32-bit floats for those 3 numbers. CPU and GPU performance is now such that you can do calculations in that space. So really this 64 to 940 business is really talking about the interface on the way in, and often, at least in the case of an HD shoot, the interface, or I should say HD deliverable, the interface on the way out. I call these interface codes, and I call the 64 the interface offset. And if you speak with anyone who's really familiar with the guts of the arithmetic in grading, they will tell you that the first thing that they do is subtract 64 from those HD input numbers, because they just want to treat black as 0. So don't be confused by people who seem to know a huge amount of technical detail about HD. Really what's important is the concept. Now, we can have we've already had a little bit of a discussion, and later in the course we'll have further discussion about codes larger than reference white and codes in the footroom region lower than reference black. And they're useful for certain particular applications, some of which you've heard about and a few of which we'll describe in later classes. Now, the grading system, this is sort of a little bit silly to say, but grading is really just in the guts of the machinery, in the code space 0 to 1, the abstract code space, is really just y equals mx plus b, where this m is adjustable and this b is adjustable. And as I've indicated in previous classes, it's unfortunate that we've got lots of different names for those 2 variables. So in signal processing terms, you would call the m gain, but unfortunately in displays, this is often called contrast. And that control does not affect visual contrast. So let's not use the term contrast. And in fact, in grading systems, the word gain is used quite often. Now, B, from the point of view of math or science or signal processing, you could call it a bias or an offset. I like the word black level. But in displays, it's often called brightness. And this is wrong, because that control, or that parameter, if you like, does not really control visual brightness at all. And it's common to use another term in color grading systems, not quite bias or offset, but lift. And lift just refers to lifting the signal up or dropping it down. So that's the control. But lift is distinguished by the fact that it leaves white where it sits. And so lift is really, I think if I remember correctly, mathematically, instead of having plus B, you have plus M times, let's call it L for lift. So it's still an additive term, but now the additive term lift is multiplied by the M. And that little mathematical construction basically leaves white staying put when you move the black up and down using lift. That's all that does. So it's sort of a nuisance if while you're adjusting the blacks, the whites also go up and down, and that's what happens with the bias or offset control. So we implement lift instead, and it just alters black but leaves white where it sits. Now, the other piece for grading is we've got lift, gain, and one more thing. And the one more thing is put parenthesis around that mx plus b, or mx plus m times L, and raise that to a power, which I'll symbolize by the Greek symbol, and that, of course, is the Greek symbol for gamma. Now, typically what happens with gamma is that we have a reference that just maps the input from 0 to 1 to the output from 0 to 1. But if you apply a slight power function to that, you can slightly depress the midtones, leaving white and black where they are, or even depress the midtones quite a bit. Or you can raise the midtones a little bit or raise the midtones a lot. So this adjustment, that's the gamma. And, in the way I've drawn this little sketch, very, very roughly, this would be about a square root, and this would be about a square. And this is maybe a 0.7, and that's maybe a 1.4. But you rarely find the gamma adjustment has got any numbers on it at all. And different grading systems use different scale factors, and no two grading systems do the mathematics exactly alike. But the thrust of it is basically y equals mx plus b raised to the gamma. And you've got lift, gamma, gain knobs, and the lift is associated with the offset. The gamma is here, and the gain is just the m value. Now, let's briefly review what those things do. So in the y equals mx plus b, and, I guess I'm really highly simplifying this, and some of the more sophisticated people in color grading might object that I'm oversimplifying, but it really is pretty much as simple as that. Now, you have to keep in mind, though, there's actually 3 of these equations. One for red, one for green, and one for blue. Now, really, I should have subscripts on all of these parameters as well, because these 3 parameters relate to blue, these 3 parameters relate to green, and these 3 parameters relate to red. So you've basically got 9 knobs, but they're not really exactly presented to you as 9 knobs. They're presented to you as a master, which basically controls all 3 in this. Well, I'm sorry, I'm mistaken here, because ordinarily they're presented to you lift, gamma, gain. So here the M factor, well, those are the gains. So ordinarily there's a master which is applied to all 3 of those values of M. And then there's a trackball or a ring. So the gain just goes up and down, and that applies to all 3 channels. And then there's a trackball or a ring, or historically in the old days might have found a joystick, which allows 2 degrees of freedom to control the differences among the channels, leaving the average value exactly where it is. And this is exactly equivalent to the B prime minus Y prime on one axis and R prime minus Y prime on the other axis that I showed you in Lumicolor difference encoding. So this space of making these differential equations is very much like operating in CBCR space. And so this is why I inserted the CBCR class in front of the grading class. So by manipulating the differentials, you change one channel but not the other channel, or you change one channel up and another channel down while leaving the average the same. And that principle of the master, and I don't know what to call this. I want to use the word differential because I'm kind of a mathematician at heart. But that word is not a word of art. That's just my mathematical description for what that does. So you've got those differential controls on each of the three channels. So here's your 9 degrees of freedom. You've got 3 degrees of freedom in the master control, and then 2 degrees of freedom in each of these typically trackballs or disks. Now, what do these things do visually? We really got to talk about that. So lift, as I mentioned, changes the black, but leaves white where it sits. And earlier, in an earlier class, I explained to you that I really, you could call this black level. I mean, it's where black as sensed by the camera is delivered in the output space on the scale of black to white. So you can take a black image from the scene by the camera and make it lighter or darker as appropriate. And I gave you the example in an earlier class of removing mist. If you've got a long telephoto shot of a distant mountain, it's really particulate matter or suspended water droplets, mist, fog, in the path between the object and the camera that scatters light. It scatters light from your subject out of the path to the camera, and it scatters atmospheric light and skylight into the path of the camera. It raises the black values as seen by the camera. And so you can dial those out by dropping the lift. And that, in essence, in that example I've shown you, removes the mist. And I used this joking term in the previous class, murkiness. You can dial murkiness out of the image, and you can also dial murkiness into the image by raising the black level as if there's mist in the scene, even though there actually wasn't mist when you shot it. So that's the sort of thing that lift is used for. There's no good single word description for that, and the really expert super good colorists are probably going to object to my word. But I'm going to call it murk, dial it in or dial it out. Now, gain is controlling the peak value of red, green, and blue. So if I kind of go back to a spectral diagram, 400 to 700 nanometers, you've got red, green, and blue. The gain control is really affecting how much optical energy is delivered in each of those bands. And so I can deliver more red and less blue. Well, that obviously makes the picture look red-ish. So if for aesthetic reasons I want a reddish looking picture, I will just dial up the red gain. And you have to figure out, it's not standardized which direction is which, but often this will be blue and this will be red. So dial red into the picture using gain. Won't do anything to the blacks, won't affect the murkiness, but it will simply make the picture more red. And a very, very common use of the gain control is just white balance. Because if, when the image data came in from the camera, if the scene was lit by tungsten light, tungsten is really deficient in the blue. So you would very commonly use the gain control to dial in some blue gain and dial out some red gain to neutralize the red, the green, and the blue to make a gray instead of a red. And that's just color balancing or white balancing. The gain control is useful for that. So I'll just stick with the word gain here because that's the word that is on the panel, and it's sort of mathematically intuitively correct. The master gain, you could call that visual brightness. And I'm putting that in lowercase letters because you won't find that written on the face, labeling any knob. Because the brightness knob is actually controlling this. Now, gamma, what does that do? So I've already explained that gamma is basically taking this reference mapping that's just a straight line from 0 to 1 and allowing you to increase the midtones a little bit, leaving black and white where they are, or decrease the midtones a little bit. And visually, so let's see if I can correct my diagram here to go, well, let's just relabel 1. Sorry, we'll put 1 here. So you can think of the dominant effect of the gamma control being at the midtones around 0.5. And you get to move those midtones over a huge range of the output without altering black, without altering white. Visually, this maps to contrast. It's visual contrast. Dialing the power function to lower levels of gamma yields more visual contrast, and dialing it to higher levels yields less visual contrast. So more contrasty, less contrasty. And again, this is sort of craziness because the visual effect is contrast. But on a piece of video processing equipment or even on a video display, this knob is the one that's labeled with the word contrast. So it's all super confusing, and I wish we could just fix it, but it seems too late for that. So those are the main 3 controls, and if you just use the master controls, your adjustments will affect the image in all colors equally. But then there are other things you do, like if you drop the gamma of one channel, but by using the differential control, leaving the other 2 channels the same, it can have the effect of changing the color in the midtones, but leaving the black color black and the deep grays neutral and the whites white and the highlights neutral. So you can change the color of the midtones. And this has become sort of signature visual style, this idea of having blue shadows and orange highlights, for example. It can achieve a visual style, but it doesn't really have any justification in terms of signal processing or color science. It just imposes a visual effect. So that's what happens with gamma when you use gamma differentially. Gamma, the master gamma control, just basically dials in or out contrast, visual contrast from the picture. So there's your story about the basics of color grading. And there's 1 or 2 things that I need to describe loosely related to this in terms of cameras. Because cameras, HD cameras, historically, have got controls like this built into the camera. And so the videographer, cinematographer, DOP can, if they wish, dial in such things at the camera. But as I've indicated at the top of this class, you really don't want to do that if you're in a VFX show, because you will be unable to dial them out on a reliable basis. And also, more bad news, displays have typically got comparable controls to all of these built in as well. But really, we don't want the displays to do anything. I mean, really what we want is we want to capture, or let's say acquire, ship it into the grading system. We want to make adjustments here, which are, some of the adjustments are to dial out errors that were made. Some of them are to deal with technical issues like what coding scheme did the data arrive in. You know, was it studio range or full range, for example? Those sorts of adjustments can be accommodated by these controls. But once we deliver, we really want to think about doing grading as using a reference display to get the picture we want. And when we approve that and sign off on it, downstream is just science. So when that imagery goes to a downstream display, we don't want the display to be messing around with things like this. Or if the display is not stable or repeatable, doesn't have accurate factory settings out of the box, then a display calibrator might go and mess with these knobs to do science. But from the point of approval downstream, this should all be science, where grading really involves some craft and some art. So we'll come back when we talk about cameras and talk a little bit about what camera controls are available, but that's the basic conceptual picture behind what's going on in color grading.